Hello everybody. Today we're going to be talking about displaying quantitative data. Remember, quantitative data is numbers that you can count and do arithmetic operations with. So the first thing we want to talk about is a way to display quantitative data, and that would be with a dot plot. A dot plot shows each value as a dot above its location on a number line. An example of that would be how many students are in Miss Guilford's classes. So as you can see, these numbers range from 4 to, I believe this is 21. And you can count the number of dots to see how many kids are in each class. If you guys want to know where this graph came from, I will try to put it into the description for this video so you guys can use this for your future graph making. So let's do an example. So how much would you pay for fun? So Noble's Amusement Park in Ellisburg, Pennsylvania has earned acclaim for being an affordable, family-friendly entertainment venue. Noble's does not charge for general admission or parking, but they do charge customers for each ride they take. How much do the rides cost at Noble's? The table below shows the cost for each ride and a sample of 22 rides in a recent year. Make a dot plot of these data. So the first thing we're going to do is we're going to label. So we're going to say that this is the cost of a ride. Okay? And then what we're going to do is we're going to try to see what our lowest number is. And it looks like our lowest number is $1.25. So what we'll do is we will put 125 down here. And it looks like they go up by quarters until you get to, it looks like $3 right here. Okay, so what I'm going to do is I'm going to do 150, 175, $2, 225, 250, 275, and $3. Now, hopefully yours looks a little bit better than mine. I'm a little messy with the handwriting. So what we're going to do now is we're going to see how many are in each category. So how many rides can you ride for $1.25? Well, for $1.25, we have 1, 2, 3, 4, 4. So that means we're going to put in 4 dots. So we have 1, 2, 3, 4. And they don't have to be dots. They can be symbols or stars or squares or X's, whatever you want them to be. Just because it says dot plot does not mean it always has to be a dot. So now we're going to look at $1.50. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we're going to put 8 dots. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, and please notice that these first 4 that I have going on here, I'm trying to make sure that they're same height, because if you start making these dots bigger or smaller or further apart, it's going to actually skew what the whole graph looks like. So next we have $1.75. So we have 1, 2, well, let me cross it off, 2, 3, 4, 5, 6 dots. So that means we're going to put 1, 2, 3, 4, 5, 6 dots at $1.75. Now we're looking for $2, and it looks like we only have one $2 ride, so we're just going to put 1 dot at $2. If you look through all of these numbers, there are actually no rides that cost $2.25 to ride, so we're going to leave that space blank here. Now for $2.50, it looks like we have 1 and 2. So we have 1, 2 dots at $2.50. Again, we don't have anything at $2.75 looking at all of these numbers, but we do have our last guy right here, $3. So this is our dot plot of Nobel's amusement park rides and how much they cost. So you might also want to make sure that you got everything by checking how many dots there are here. There's 12, there's 18, 19, 20, 21, 22, and we have 22 rides. So it's always good to go back and just make sure that you have everything that you need. Dotplots hopefully will be nice and simple for you. Now, how to describe the distributions of quantitative variable. Now, I always tell you to remember your socks, like the socks on your feet. So the first S stands for spread, and that gives the lowest and highest values of the data set. Okay, there are many different ways to describe spread. Right now, we're going to use range as a way to describe spread, but as we go throughout the chapter, we're going to learn other terminology for this measure. So O stands for outliers, and outliers are any values that stand out more than others or stand out as unusual. Now, an outlier in any graph or data is an individual observation that falls outside the overall pattern of the graph. Now, outliers actually have a formula, and we'll be able to actually find them mathematically in the upcoming chapters. But right now, we're just looking to see if anything kind of sticks out. The C stands for center, which is the approximate average value of the data, and it's only an estimation right now. Eventually, we will find out other ways to measure center using methods such as mean or median, but right now, we're just kind of looking at what is the balancing point of the graph. And last but certainly not least, we have shape. Does the graph show symmetry? Is it skewed in one direction? Well, let's see. So if it's roughly symmetric, you'll see that it kind of comes up and then it kind of comes down, right? So it looks pretty symmetric. This one isn't actually 100% symmetric, but to the eye, it looks pretty symmetrical. Then we also have skewed to the right. So it comes up over here, and then this tail kind of drags off towards the right. And then we have skewed to the left, where it kind of comes up over here, and the tail skews off to the left. Now, I always remember whether it's skewed to the right or left, depending on where the tail is, okay? I don't know why, but over the past years, we kind of like draw little monsters in here, and it's running away from the skewedness. So if it's skewed to the right, it's actually the monster it's running away from is right here. We can pretend that's me with a math test. Okay, so skewed to the right means the tail's on the right. Skewed to the left means the tail's on the left side. So a stem plot is, it shows each data value separated into two parts. A stem, which consists of all but the final digit, and a leaf, which is the final digit. The stems are ordered from least to greatest and arranged in a vertical column, and the leaves are arranged in increasing order out from the appropriate stems. Here's an example of a stem plot. Okay, so the most important thing you need to see on this is the key down here at the bottom. And if you see 1 line 0, that actually refers to a data set of 10. So if we take 3, 5 here, that is actually really 35. So if we were to start to list out these numbers, it looks like you would get 4, 6, 12, 14, 18, 33, 34, 34, 35, 35, and so on and so forth. Okay, I think you guys have all seen stem plots before, or stem and leaf plots, whatever they're calling them. It's going to look like this. So let's see if we can do an example. So the table shows the masses in grams of 17 unwrapped Snickers fun size bars taken from one bag. I want to make a stem plot of this data. So what I'm going to do is I'm actually going to create a stem plot that starts at 15.9 and ends at 19.2 because those are the two largest and the smallest we have here. So the first thing I'm going to do is I'm going to try to figure out how I'm going to break this up. So it looks like these are all 2 digits with a decimal point. So because it's going to start at 15.9, I'm going to start my stem and leaf plot at 15, and I'm going to make it go all the way up to 19 because we have 19.2. Okay, so down here, I'm going to make a little key on how we're doing this, and I'm going to say that 15 line 9 is equal to 15.9 grams. Okay, so here's our little key at the bottom. So now we're going to know how to read this. So first we have 15.9, and so we have 15.9. I don't think there's anything bigger than that, smaller than that. So the next thing we have looks like it's going to be 16. Now there's no decimal place here, so it's going to be 16.0. Okay, now we're looking for the next biggest number, and it looks like it's going to be 16.5. And there's two of them. So now we have 5, 5. The next biggest number looks like it's going to be 16.6. So we're going to put a 6 here. And then we have 16.7. So we have a 7. And last but certainly not least, in the 16s, we have 16.8. So we're going to put our 8 there. Okay, so we found all of the 16s. So now we need to go on to the 17s. And it looks like the smallest 17 we have is 17.1. So we have 1, 2, 3 17.1s. So you're going to have 1, 2, 3 17.1s. Okay, and notice I'm trying to space them out just like the ones above them so that we can get a good, accurate look at our graph. Okay, so the next thing we're going to be looking for is, it looks like 17.3. Okay, and it looks like we only have one 17.3. And then it looks like we have a few 17.4s. So we have 1, 2. So that's going to be reflected over here. 1, 2. And then after 17.4, it looks like we have two 17.7s. So we have 1, 2 7s, and then a 17.8. Okay, we don't actually have anything in the 18s, so this whole 18 row right here is going to be completely blank. But don't forget, we do have that 19.2, and we're going to put that right here. So this is actually our stem and leaf plot for this data right here. Now, there's another type of stem and leaf plot that you could do. It's a split stem and leaf plot. You would split large amount of data. Maybe if this was a long row, might be good to look a little bit deeper into the actual stem and leaf plot. So the way you would do that is you would break it up into highs and lows for each category. So you'd have 15 low, and then you would have 15 high, then you would have 16 low, 16 high, then you would have 17 low, 17 high, and then you would have 18 low, 18 high, and then you would have 19 low, 19 high. Now, the low parts are from 0 to 4, and the high parts are from 5 to 9. So let's look back over at our first graph instead of looking back over at this mess here. Okay, so we have 15.9 as our first one over here. So because 9 is between 5 and 9, we're going to put it in our high category. Okay, now we're going to look at 16s. And remember that lows go from 0 to 4. So that means we're going to have a 0 here, and the rest of these numbers are going to go into the high category. Okay. Now for 17, remember that the low is between 0 and 4. So we're going to have 1, 1, 1, 3, 4, 4. And our highs would be 7, 7, 8. Now again, we have nothing for our 18s. But for our 19s, we still have that 19.2, which is low. And what this actually does is it kind of gives us a zoomed in effect to our stem and leaf plot. So if we really want to get a good look at the distribution, sometimes we could do a split stem graph just like this so that we know what the actual shape of the graph looks like. And again, always remember to do a key. Okay, it will tell you whether you have to make a split stem graph or not. So there's not going to be any surprises. So, hold on. I seem to go. Okay, so you can actually use another type of stem plot, which is a back-to-back stem plot with two common stems to compare distributions of a quantitative variable in two groups. So this is an example of two things being measured between males and females. So just notice that the right side is males, and that's read like a normal stem plot, right? But the left side, because we're going from the inside out, is read just a little bit differently. So in this case, this number right here is read 0, 2. This number right here is read 29 or 29. This number right here, well, that's going to be 44 no matter which way you look at it. But this number right here, 5, 4, you're reading out. So 54, as you can see reflected down here in the key. Ooh. Okay. So how many shoes are too many shoes? Okay, so how many pairs of shoes does a typical teenager own? To find out, a group of students surveyed separate. Wow, that's a tongueful right there. A group of statistics students surveyed separate random samples of 12 female students and 12 male students from their large high school. Then they recorded the number of pairs of shoes that each person owned. So what we're going to do is we're going to make a stem plot of these data. Now, hold on. So what we're going to do is there's going to be numbers in the middle, and then one side is going to be females, and the other side is going to be males. So it looks like the smallest amount of shoes that anybody owns is 5. So we're going to start out with 0, and then 1, 2, 3, 4, 5. Why did I stop at 5? Because I believe the largest number here is 57. Okay, so what we're going to do is we're first going to start out with the females, and we're going to see if any of these females have single digits of shoes, and that is a big no. So now let's look at what is in the teens. So we have 13, 15, and 19. So that means we're going to have 3, 5, and 9. Okay, so I think that's it in there. So now we're going to look at the 20s, and it looks like we have 22, 23, 24, and then 2 26s. Okay, then we have the 30s, and it looks like we have 31 and 38. So that means it's going to be 1 and 8. It doesn't look like we have anything in the 40s, but we do have 2 in the 50s. We have 50 and 57. So I'm just going to count that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have all 12 females here on the left side. So for our key, we have 1 line 3 is equal to 13 shoes. Okay, now let's look at the males. Now it looks like our smallest number again is 5. So we have 1, 5, and then we have a 6. It looks like we then have 2 7s and an 8. Okay, so that's all we have for single digits. And then for the 10s, it looks like we have 2 10s. So 0, 0. Then we have an 11. We have a 12. And it looks like we have a 14. I don't think there's anything else in the teens. For 20s, it looks like we have a 22. And that's it. And then for 30s, we have a 38. So we need to write another key for this side. And let's say we did 8 line 3 is actually 38 shoes. Okay, so we've made a stem plot of the data. Now we want to describe the shapes of the distribution. So when you're looking at a distribution, I like to draw these little lines here. And if you turn it sideways, you can kind of see that this is slightly skewed to the right. So the female, or the distribution of female shoes, is skewed slightly to the right. Now, if you look at male shoes, we have a lot higher here, and then it also kind of comes out there. So you got to remember that this is kind of reversed. So this is actually also skewed right. So there are fewer people with more shoes, as is the distribution of why does it say poop there? Oh, goodness gracious. Hold on just 1 second. Well, that was interesting. Let's go back in. Okay, so what do we have here? As is the distribution of the males' shoes. Oh, boy. Now, if you wanted to see a little bit more of a clearer distribution, you could split the stems, but here we just have so many that we just decided not to. So let's look at another type of way to display a quantitative data. So another way that you may have heard of is a histogram, not to be confused with the bar chart. We're going to go over that in just a second. So a histogram shows each interval as a bar. The heights of the bars show the frequencies or relative frequencies. Remember that frequencies is count and relative frequencies is percent or proportion of the values in each interval. We're going to follow the steps when making one by hand. So the first thing we're going to do is we're going to choose equal width intervals or bin widths that span the data. 5 intervals is usually a good minimum to start with. We're going to then make a table that shows the frequency or relative frequency of the data values in each interval. And then we're going to draw and label the axes. We're going to scale the axes and then draw the bars. Okay, so what we're going to do is we are going to do an example. Now, I used to do this example with 40 male skulls, but now I kind of limited it to 12 just because the other one was extremely time consuming. So I'm going to look here to see what we have. It looks like our minimum is at 119 and our maximum is at 139. So what we're actually going to do, what we should probably do is read the question first. So we have example number 7. What can we learn from the past? So ancient Egyptian embalming techniques and the climate in Egypt can preserve bodies of the dead remarkably well. Researchers made measurements of 12 Egyptian male skulls that date back to 4000 BCE. One variable they recorded was the maximum width of the skull in millimeters shown in the table. We're going to make a frequency histogram of this data. So what we're going to do first is we are going to create bin widths. So we're going to find some equal bin widths. And because we go from 119 to 139, I say that we go by 5s. So my first bin width is going to be from 115 to 120. Okay. And then we're going to go from 120 to 125, then 125 to 130, 130 to 135, and then 135 to 140. Now we're going up to and including this number here. So we're actually going larger than 120 here, and you're going to see what we're going to be doing in a second there. So how many numbers are between 115 and 120 inclusive? That answer would be 1. We have that 119. Okay, so then we want to ask ourselves, how many numbers are between 120 and 125, including 125? So we look here, it looks like we have 1. And then we're going to go from 125 to 130, including 30. So let's look here. We have, right here, we have 126. Okay, and then we have 130 to 135. So that's including 135. So we have 1, 2, 3, 4, 5, 6. So we have 6 here, and then we have 135 to 140. We have 1, 2, 3. Okay, so now we know how many bins we have. We have 5 bins, 1, 2, 3, 4, 5. Okay, we made a table that showed all the frequencies or relative frequencies. We chose frequencies for this one. And what we're going to do now is we're going to draw and label the axes. So down here at this, the x-axis is going to be skull width in millimeters. Okay, and remember we started all the way from 115, 120, 125, 130, 135, 140. Okay, and then over here is going to be the frequency. And I'm going to try to draw sideways here. Frequency. Okay, and it's between, what do we have? 1 and 6 here. So let's just go by lines. 1, 2, 3, 4, 5, 6. Okay, so we've now labeled the axes, and the next thing we want to do is scale them, which we just did. And now the last thing we have to do is draw the bars. So what I'm going to do is I'm going to start here at 115. I'm going to come up to 1, go all the way over to 120 and down. So what this basically is saying is that I have one skull width that is between 115 and 120 inclusive. Okay. The next one here, we have between 120 and 125, we have another 1. So we're going to draw another line. Now, I just noticed that these are a little bit off. You're definitely going to want to keep them nice and equally spaced. Okay. So between 125 and 130 inclusive, again, we have 1. And I realize that these are just getting smaller and smaller. That is my bad. Between 130 and 135, we have 6. So we're going to go all the way up here where all the bars are touching. Come on over, come back down. And the last one is at 3. So we're going to come up from 135, come down, and come down like that. So now we have a histogram of the maximum width of Egyptian male skulls from 4000 BCE. And as you can look at this, you can do your SOCS if you have to. You can see that your spread is from 119 to 139. Your outliers, there doesn't seem to be any outlying points here. Your centers looks like it's somewhere between 130 and 135. And the last thing is the shape, and it looks like it's skewed to the left slightly. Okay, let's try one more example. Okay, I just realized to say okay a lot. I apologize for that. So example number 8, which is the stronger picker-upper? So in commercials for Bounty paper towels, the manufacturer claims that they are the quicker picker-upper, but are they also the stronger picker-upper? A random sample of 30 Bounty paper towels and a random sample of 30 generic paper towels and measured their strength when wet. To do this, each paper towel was uniformly soaked with 4 ounces of water and counted how many quarters each paper towel could hold until ripping, alternating brands. Compare the distributions as revealed from the following histogram. Now, in order to talk about and compare the distributions, we are going to have to talk about their SOCS. Now remember, the first S is the spread. So let's look at the spread here. The spread of the Bounty looks like it held anywhere from 100 quarters to 130 quarters. So it looks, so that is about 30 quarters. Okay, and if you look over here, this looks to be about 76 to 104, and that gives you, what is that, 28 quarters? Oh my goodness, it won't let me write the 2. Okay, 28 quarters. It will not let me write that 2, but you guys all heard it. So we're going to say that the variability or range is very similar. And remember, we are comparing these, so you have to use comparing words. And what I would say is very similar, but the bounty is slightly larger. Okay, now we're going to look at both of these. And is there anything that kind of pokes out? Is there anything that looks a little out of the ordinary? And the answer to that is no. There doesn't appear to be any outliers. So that's what we're going to say. There does not appear to be any outliers in either distribution. Okay, so C stands for center. Okay, and if you look at this, it looks like the bounty appears to be centered around 115, 116. The center is somewhere in here. Okay, for the generic brand, it looks like their center is around 90. And this is just, I'm kind of going off by eye. We're going to figure out ways how to find this actually by math a little bit later. So that's what we're going to say. The center for a bounty is much higher at approximately 115 quarters to the generic which is at approximately, what did we say that it was? At 90? Approximately at 90 quarters. Okay, and the last thing we need to look at is the shape. So let's look at the shape of both of these. So if you look at the bounty, it looks like it's just ever so slightly skewed towards the left. And if you look at the bounty, it's almost roughly symmetric. Okay, so that's what we're going to say. The bounty, paper towels, has a slightly skewed left distribution, while the generic is roughly, and we use a lot of Lee words in this class, I'm sure you'll realize that, symmetric. Okay, because you can't be 100% sure one way or the other. So this is a full description of comparing two distributions to each other. Okay, so you have to go through your SOCS and you have to use comparative words. You can't just say, for let's say the center, bounty 115, generic 90. You're not comparing the two. You have to use words like higher than, more, less, equal, things like that. Okay, so that is actually the end of today's lesson. So you're going to go back to Google Classrooms and you're going to complete the next part of your assignments. And if you have any questions or concerns, you guys know that you can always contact me. Have a fantastic day.